Okay, and now I'm going to share the whiteboard. Just let me know once you are able to see the whiteboard, okay? Yes, Emma, is the screen visible?
Yes.
Okay. Um, right. So we are talking about, we are going to discuss complex numbers. Right. So, like, I assume that you have no idea about complex numbers and you have not studied this in A levels, right, Ahmed?
Yes.
All right. So that's completely okay. So, complex number is a number which is written in the form x plus iota y. Okay. Whenever you see such a form, whenever you see this iota, just know that your number is a complex number, right? Okay. Now, here, this thing is basically the real part, and this basically is the imaginary part. And I'll give you a little background about complex numbers, right? So, whenever you are, you know, calculating something, and if you come across such a number, and if you do it on calculator, you will see that there's an error, right? You cannot solve this basically cannot be calculated using the calculator as well. And like in math,
Mm.
so far we know that this is not real, right? Whenever you are
Yes.
we are finding quadratic roots, and whenever the discriminant used to be negative, we just write that no real solution. So this is correct, that whenever we have no real solution, we basically enter the complex numbers. The solution is basically a complex number, right? So let's not complicate things. Okay. So if you have minus 49 in under root, you can write this as under root minus 1 and under root 49, right? We can use this.
Yes.
And you know what under root 49 is. Under root 49 is plus minus 7, right? So let's write down 7 right now. It is 7. And if we talk about
Zero.
this number under root minus 1, this is basically iota, right? So we write it as 7 iota.
Yes.
So just know that iota is basically under root minus 1. Okay. All right. So let me just make some divisions. Okay. So far you know that iota is minus 1, right? So if I say what is iota square, because you will come across this iota square many times, and this is important. So iota square would be, you have to square both sides, this side and this side, and you will get minus
Yes.
1, right? Okay. And then if I
Mm.
talk about iota cube, this is going to
One.
be minus iota, right? And if I talk about iota to the 4, this is going to be 1. Why is it 1? Because for writing iota to the 4, we can write iota square into iota square. So minus 1 into minus 1 would be 1. So are you clear with these general forms which we will be using in questions?
No. How is it? How is?
Yes.
Tell me about the cube. What happened at the cube?
In which one?
The iota cube.
Iota Q. It's not iota Q, it's iota to the 4. Wait.
No, I'm talking about iota cube is equal to minus iota. What happened there?
Oh, iota cube. Sorry, iota cube. Okay, definitely. I'll explain. Okay, look. So we know that iota square is minus 1, right? We want
Mm.
iota cube, so I will multiply iota on both sides. Yes, so if I multiply iota on both sides, I am going to get iota square into iota into iota. So iota square into iota would be iota cube. This equals minus iota, right? Like we will use
Okay,
this for
it
finding
wouldn't be
this.
like taking cube on both sides. That wouldn't be the case, right?
If we take cube on both sides, that way things would, become very complicated, but you can do that way as well. Let's do it that way as well, because in maths, we can do things in any way like that. We should also get correct answer. Okay, so you want to use this, right? So if we use iota cube equals under root minus 1 cube, right? So iota
Mm.
cube would be under root minus 1 into under root minus 1, again under root minus 1. So this basically is going to be under root minus 1 into minus 1 under root minus 1. Minus 1 would be 1 and under root 1 would be 1. So we have 1 into under root minus 1. So this under root minus 1 is basically iota,
Okay.
right? So these are general properties, and the most important one is this one. Just focus on this part, okay? This is the most important one, and you should be familiar with this, right?
Yes.
Okay. All right. So let me just rub the extra things just so you can just, just note down these four directly. And this is the most important one, so this should be on your fingertips, okay? Right. So far
Yeah.
we know that any complex number can be written as real plus imaginary part, and the part which is coming with iota is basically the imaginary part, and this is the real part, okay? Then we have discussed some of the general iota forms which are important for questions, right? So these are two things. And I'll give you a quick example. So when we talk about complex numbers, we can have z equals 2 plus 3 iota. We can have z equals 4 plus 10 iota, right? So this is how we have complex numbers. 1 plus 4 iota. So this is basically the real part. This is the imaginary part. But these numbers are mathematical numbers, okay? Don't get confused by this and this definition. The only reason behind saying this real and this imaginary, because here we have iota thing. So whenever we have iota, we know that this iota is under root minus 1, and we have not been dealing with this so far because this is not correct mathematically, and this gives no real solutions. So mathematicians wanted, they did not want to stop at a point, so they defined and or discovered this new branch of maths which has complex numbers, just so we can do further researches and we can do whatever we want to, right? So is this background and everything clear?
Yes.
Okay. All right. Then we have, let's say, if z is a complex number x plus iota y, if I talk about z bar, this basically means conjugate. Okay, this basically is conjugate of z. Okay, z with a dash on top is basically conjugate of z, and this is what it would be: x minus iota y. So the only difference in z and z conjugate is of the sign. Okay, if we have x in z, we will have minus in z conjugate, right? And if we had x equals x minus iota y, you will have z conjugate as x plus iota y. Okay, so just know that you have to multiply a minus sign uh, over here with the imaginary part, and you will get your z conjugate, right? So is this thing clear? Are you clear with this?
Yes.
All right, all right, okay. And then the final thing is that if this is z, if this is z conjugate, what if I talk about the conjugate of z conjugate, right? So this again would be like this is my z conjugate, that is x minus iota y,
Mhm.
and the
I will
conjugate
be
of
plus.
z conjugate would be x plus iota y, which basically was my z. Okay, so you should know that z conjugate is basically z.
Okay, understood.
Say it again.
I said understood.
Okay, very good. Right. Okay, so we are done with this as well. Okay, we only left with a few properties and then we can discuss questions. Right. Then you should know what modulus and argument of a complex number is. Okay. All right. So for that, I should use graph. Okay. So although we're talking about complex numbers, but we can define these complex numbers on graph as well. Okay. So this is going to have this is going to be the imaginary axis, and this is the real axis, right? So numbers would be in this form. Iota, then we will have 2 iota, 3 iota, 4 iota, and here we will have like normal ones, 1, 2, 3, and so on. Okay, right. Now if I talk about z equals x plus iota y, this is a complex number. Okay, and I can write it as xy, right? This is going to be the pair. Why am I mentioning it this way? You'll just get to know, because you know in graphs, on graphs we have points, we have random points, and every point has an x coordinate and a y coordinate, right? So this is why I've written noted down in pair. All right. So let's say we have z equals 2 plus 4 iota, right? This is the point. Let's just find this point on graph. So this is the real part and this is the imaginary part. So 2 on real is here. This is my 2. And then we have 4 iota, the imaginary part is here. So this would be the point, right? Are you
Yeah.
clear so far? Okay. All right. So you are clear so far. And here we basically intend to discuss modulus and argument of a complex number. Okay. Now, Ahmed, these are the only things we are left with of complex numbers, right? So, modulus and argument, right? So, this is a graph, and on this graph, I'm saying that this point is basically 2 plus 4 iota. Okay, now if I say that modulus is basically the distance from origin to this point, so how are you going to find this distance? If we talk about simple maths, how are we going to do that? So if I think of it as a triangle, right? If I draw this triangle here again, with this is the side, and then we have this x-axis side, and then the y-axis side, right? So I want this distance, and this distance is basically the modulus. So this length is 4 iota, and this length is basically 2, right? Are you clear?
Yes.
Right? So whenever we have to find this distance, what we do is we just square these two numbers using the Pythagoras theorem, right? So we square this number and we square this number, right? Just give me a second. Let me just remove these iotas because this is going to confuse you with this thing. All right, wait. This is 1, 2, 3, 4. So this was 4. This is 3. 3, 2, and 1, right? Okay. Okay. Just know that we write the whenever we are saying this as imaginary excess, this is basically 4 iota, 3 iota, 2 iota, and 1. The reason behind removing these iota is that we define modulus in this way. Mod of z is basically denoted as this, and we basically square the real part and the imaginary part, right? So we are not squaring the iota. So since I am explaining this through the triangle, through the Pythagoras theorem, so I just wanted to tell you that we only square the real and imaginary parts, right? So this is how you define mod of z, and this is the reason why we do it this way. Because if we talk about the graph of complex numbers, we have imaginary part on x-axis, on y-axis, and real part on x-axis. And again, if this is 2 plus 4 iota, so this is 2 and this is 4, and when we talk about mod of z, it basically is the distance from origin to this point, right? And I tried explaining this using the Pythagoras theorem that since this length is 2 and since this length is 4, so we know that we square the two small sides and we get the third one, right? This one, which was basically
Okay.
the third side, let's write it as x, okay? So this is how in general you define mod. If you have a complex number x plus iota y, this is how you define its mod. Z equals x plus iota y, right? And the final thing is argument. The final thing is argument. So for argument, we write for argument we write arg of z, that basically is tan inverse y by x. Okay, and why is it tan inverse y by x? Like, do you have any idea? So basically, if I tell you argument is this angle, argument is the angle between this line, which we get when we join the origin and this point of the complex number, and between this origin, right? Between this x-axis. So the angle between x-axis and this line is basically the argument of z, right? And if we talk about the trigonometric ratio, so we have tan theta equals perpendicular over base, right? So this is the right angle here. Perpendicular side is the y1 and base is the x1. So since we want this theta, since this theta is the argument, so what we do is theta equals tan inverse y by x. So even if you are not clear with these explanations, you should just know that the argument of z is basically calculated by tan inverse y by x when this is your complex number. So are you clear with this?
Yes.
All right, perfect.
Good.
So
You will be
anything?
sharing notes, right, after the class?
Yeah, definitely. I will share. I will share.
Okay.
Okay, so anything which you would like to ask?
Yes, one thing. There's a thing that has been going on my mind, okay?
Yes.
When I saw the graph. Have
Okay.
you studied infinity?
Sorry, what?
Have you studied infinity?
Infinity?
Yeah.
Yeah, like you're talking about this?
Yeah, the infinity, yes, yes.
Yeah, okay.
So we know that between 1 and 2 there is infinity, right?
Oh,
Infinite
okay.
numbers,
Yes,
right?
yes,
But
yes,
but we have the boundary too.
yes. Very good. So,
So what is that supposed to mean? Like we have the boundary. We know there are infinite numbers, but
mhm.
there is a boundary.
Yeah. So, okay, I'll tell you. Okay, that's a very good question. But this thing again, this thing holds for real numbers only. If we talk about the set of real numbers, and if I talk
Mhm.
about the number line of real numbers, okay, okay, let me just rub everything and then I'll explain this. Okay, right. So, this is for real numbers. This is for, let's say, natural numbers. This is for integers. Okay, so we have like three number lines. In this case, if I talk about, this is for real numbers. Let's say this is 0, then we have 1, we have 2. Okay, let's say this one is for sorry, natural numbers. We do not have 0 in natural numbers. We have 1, then we have 2, we have 3, and so on. And if we talk about set of integers, instead of integers, I have 0, I have 1, I have 2, so on. I have -1 and I have -2. Right. So everything is clear. For natural numbers, we only have such numbers. For real numbers, we only have such numbers. But when we talk about real numbers, between 0 and 1, I am going to have 0.0000000000000000000 so on 1. Then I'm going to again have 0.00 so on 1. Right? So when we talk about real numbers, I told you we every number in maths which you studied before this class, like before discussing complex numbers, is a real number. No matter if it is a
Mm.
decimal number, if it is a fraction. When we say that every number in maths is a real number, between this 0 and 1, we are going to have infinite many numbers, right? Like there's no limit. Although you are 100% correct that 1 would be the boundary, but between this 0 and 1, I am going to
Mm.
have all these numbers, right? I will have
Right.
0.0001, then 0.00001. So I cannot specify the number of zeros I am mentioning between the point and the 1.
Exactly.
That can be infinite many. Okay?
Yes. But
Okay.
there is
Yes.
that boundary. But
Yeah, this
that
one.
means there is that ending point.
Yeah, yes, yes. This one is the ending point. Yes.
But this okay, we can discuss this later.
Yeah, but just know, by saying that we have infinity between this means that we have infinite many numbers. Okay?
Infinite, yeah.
Yeah, this is what they try
Yep.
to say. And this only holds for real numbers. In natural numbers, after 1, I have 2. I don't have any number between 1
Yes.
and 2. If I talk about integers, after -2, I have -1. But in real numbers, we have every number of math. So we will have every decimal number between 0 and 1, right? So, yeah. So, are you clear with this?
Yes.
Okay, very good.
Yes.
And very good question as well. And I don't mind such questions. All right, so I will again share the other tab, right? I
It's
need,
beyond their imagination.
yeah, some things in maths are beyond our imagination, but it's okay. We should think this way because only then, our minds grow, and only then people are able to discover things. You have to think this way,
Hmm.
right? Okay, so this is basically the final thing which you should know about complex numbers. Okay, right. So here, equality of complex numbers. Whenever we say that two complex numbers are equal, that is, if this is a complex number and if this is a complex number, they can only be equal when real part is equal to real part, that is A is equal to C, and when their imaginary part is equal to imaginary part, when B is equal to D, right? So is this thing clear?
Sorry, can you repeat it? I was
Yes, yes.
coughing.
Yeah. Okay. So we're talking about equality of complex numbers. Okay. we have two complex numbers, let's say a plus iota b and c plus iota d. These two complex numbers are equal only when the real part, that is a and c, a is the real part of this complex number and c is the real part of this complex number, whenever they are equal and whenever their imaginary parts are equal, like b and d is equal. So only then these two complex numbers are equal. So let's say you have a complex number a plus iota b and another complex number c plus iota d. They can only be equal when their real parts and imaginary parts are equal, right? So real part is a and c and imaginary part is b and d. So when they are equal, the complex number would be equal, right? So is this thing clear?
Yes.
Very good. Then addition of complex numbers. So for adding complex numbers, you should know that you can only add real part and real part. Like if this is a complex number and if this is a complex number, you can only add real and real, and you can only add imaginary and imaginary, right? So you have only added real and real, imaginary and imaginary, right? So is this thing clear?
Yes.
Okay. So these things are very basic. Right. And then we have you can also think of this as vectors, right? When we talk about vectors, we add the iota component in iota only and the k component in k only, right? So this is how you can think of this as well. Like in physics, you must have in maths also we have vectors. So yeah, okay. Then we have the third property, that is scalar multiplication of complex numbers. By scalar multiplication, it means that this is a complex number and you multiply a scalar number. You know that again, it's like vectors. So scalar is basically a number that is simple mathematical number. It could be a constant and it is not a complex number. So this can be multiplied to both the real part and to the imaginary part, right? Are you clear with this? You have
Can
a
you repeat
number.
scalar?
I'll give you an example. Let's say we have 2 and we have a complex number 3 plus 4 iota, right? So this is the complex number with which I'm multiplying 2. This 2 is k. This 2 is a scalar number. It is not a complex number. So according to the definition of scalar multiplication, I will multiply this 2 with 3 and this 2 with
Hmm.
4. So I will get 6 plus 8 iota, right? This is how I scalar multiply a complex number and a simple number. But if you
All right.
have multiplication of complex numbers, this is just like we do things in maths. We have a plus iota b and we have c plus iota d. So you will multiply ac and you will multiply. Let's do it on the whiteboard. Let's do it on the whiteboard. All right. So I've shared the whiteboard. Just let me know once you're able to see it.
Yes, I can see the whiteboard.
All right. So multiplication of complex numbers. Let's say I have. Let's say I have a plus iota b and I have c plus iota d, right? Now I have two complex numbers which are being multiplied. What I can do is I can simply multiply a with c. I will get ac. I can multiply a with iota d, a into iota d, just like we do the simple multiplication, but you will figure out something different here, right? And then I can multiply this iota b with c plus iota b into c plus iota b into iota d. So iota b into iota d, right? And finally I will have ac plus iota ad plus iota BC plus iota into iota would be iota square B into D. And I told you that iota is under root minus 1, iota square is minus 1, right? So if you write this again, AC plus, obviously you will not write this for iota. We write under root minus 1 as iota plus iota BC plus iota square is minus 1. So I can write minus 1 BD. And finally, I will have AC minus BD plus iota AD plus iota BC, and then the real part of this new complex number is AC minus BD plus I can take iota common and I have AD plus BC. So this is the imaginary part and this is the real part, right? So we write IMZ, imaginary part of the complex number, and we write REZ, real part of the complex number, right? So is this thing clear? This is how we multiply.
Yes.
Very well done. Okay. Now, if I tell you quickly, all right. Now, if we have two complex numbers, and we have to divide them. Okay, we have A plus iota B, and we have C plus iota D. So these are two complex numbers. Let's say you have Z1 by Z2, which are being divided. Now, you know, whenever you have a fraction in which you have complex number in this part, you try you try getting rid of the complex part in the denominator. And this is what we do every time we have a fraction in which we have a complex number in both numerator and denominator, right? So you have to multiply it with the conjugate of Z2. Why? I'll tell you. And you will get to know that by yourself. So what is the conjugate of Z2, Ahmed? If this is Z2, C plus iota D.
Minus.
Excellent. Excellent. Okay. So this is the conjugate, right? In maths, we cannot do like whatever we want to, but we can multiply anything with 1, right? Because multiplication is because 1 is the multiplicative identity. And even if you think it in a simple way, like we can multiply 1 with a, if we have a is basically equal to a into 1, right? We can multiply 1 with any number and that is mathematically correct. So this basically is 1. Okay, this is why I can multiply this fraction with this fraction, because I'm multiplying 1 with this fraction, right? This basically is 1, so it is mathematically correct. I can multiply any fraction in any equation if its numerator and denominator are same. So are you clear till here? Are you clear this?
Yes.
Okay. Now, why am I multiplying the conjugate of denominator? Because I'll tell you. Now we have a C plus iota D. Let's say we have A plus B and we have A minus B. So whenever we have this form where we have A plus B, A minus B, we write A
Mhm.
square minus B square, right?
Minus
So
B
if I
square.
talk about
Yes.
C plus iota D into C minus iota D, can I not just write C square minus sign iota D whole square? I can certainly write it this way, right? Right, Ahmed? C square minus this square,
Mhm.
right? Okay, and this basically
Yes.
is C square minus iota square D square. C square, since iota square itself is minus 1, so minus into minus 1 would be plus, and we have D square, right? So we have C plus D square. So the denominator would basically become C square plus D square, right? And in the numerator, we have A plus iota D, and we have C minus iota D. And multiplication is easy, but are you clear with the denominator? Because this was the new thing.
Yeah, what happened with the minus I square?
Yeah. Okay. So since iota square is minus 1, right? This is the property which we have discussed. I told you this is very important. So we have minus into iota squares. This would be minus into minus 1. That
Mm.
is basically plus 1, right? So we have plus 1. Okay. All right. This thing is clear, right?
Yes.
Okay. Now the thing which you need to understand is that here we are dividing two complex numbers, and whenever you come across such a question, our end goal is to get rid of this complex part in the denominator. This is why we multiply the conjugate here and here, because we know every time when I will multiply the conjugate of this number with it, I will get this form. And when I will get this form, I will get iota square. And when I have iota square can be like the complex part would be cancelled, right? When we have iota square, we can write it as minus 1. So finally, we have c plus d square. Now, the c square plus d square is not a complex number anymore, okay? In the denominator.
Mm-hmm.
Okay, it's not clear. Okay, I'll tell you. That's
No,
fine.
no, no. It is clear. It is clear.
Okay. All right. Okay. So
Mm.
this basically is again a into c is ac minus a into iota d would be iota ad. Then we have plus a, sorry. Well, we are done with the ac thing. Then we have um, plus iota bc, and then we have minus iota square b into d. So this would be AC minus iota AD plus iota BC. Iota square is minus 1. This would become plus BD. And finally, we can write down the real part together. That is AC plus BD plus iota BC minus iota AD. Right? So again, we have this is the real part and this is the complex part, right? So
Mm.
I'll share the notes and these are for general ones. You don't have to learn anything by heart, okay? You should be clear with the concepts only. Don't try remembering such things, not at all, okay? Just know that whenever you have a fraction where you have complex number in numerator and denominator, this is how you carry out the question, okay? You find the conjugate of the denominator number, that would be c minus iota d. You are multiplying this fraction with 1, and by 1 I mean with same numerator and same denominators, that is mathematically correct. And you are multiplying it with the conjugate of this just so you can get a square minus b square part, and finally you have real thing in the denominator, right? You don't have the complex part now in the denominator, right? So is this thing clear?
Yes.
All right, very well done. Okay, perfect. So okay, now I'll give you a quick background. In in the first class, in the very first class, we discussed a question which was of this type, where we had a complex number and the power was 6. So I told you to split it with square, square, and square.
Yes.
And this was a long calculation. And Asad mentioned that as well, that we would not be having this much time. So how are we going to do such questions in NET? Okay. So we have the Moivre's theorem. This is the last thing. Uh, okay. This is what we have. And if we talk about the theorem, so basically it says let z is x plus iota y, right? Okay. And this basically is the Cartesian form of a number, right? So are you familiar with, we have different forms. We have Cartesian form, we have polar form. Do you know all this?
Nope, never heard about them.
All right. Okay. That's completely fine. That's completely okay. Right. So, okay, I'll tell you. All right. So just know, that's completely okay. Just know that if this is a form, there's one way of writing a complex number this way, and then there's an equivalent way which is used for this theorem only. Okay. So you don't have to like know much about it. It's just used for this theorem, but this theorem is very helpful. So if this is one way of writing a complex number, the other way of writing complex number is r cos theta plus iota r sine theta. Right? And I'll tell you this as well, okay? I'll tell you this as well. Okay, now if this again is the complex thing, and if I talk about this part, let's say this is x plus iota y. This means that we will be having x here and we will be having y here. And if, sorry. And if this is the mod, right? So if we talk about this part, and this is basically the argument, this is theta, and this is the mod, right? This is z mod, right? We have discussed this already, that we define z mod as under root x square plus y square, and we define theta as tan inverse y by x, right? So this is basically the argument and this is the mod. This is the argument angle, so I've written it as theta, and this is the mod. Are you clear this till this part? We have discussed this already.
Yes.
Okay. And one thing which you can notice from here is that if this is x, here we have r cos theta, and if this is y, here we have r sine theta. So if I have to find this is a right angle triangle, and if I want to find this x, how am I going to find this x? Okay. So
Hmm.
basically, we can use cos, right? This is what we are going to have. Okay. And what is the base? Base is x,
Hmm.
and hypotenuse side is z mod, right, Ahmed? This is the
Yes.
hypotenuse side, this is the base, and this is the y. Okay, and this is the perpendicular side as well. And if I have to find this side, I will use sine theta, and perpendicular side is basically y, and again the hypotenuse is z mod. So can I not just take this z mod over here and write it this way, and again take this z mod there and write it this way? So this z mod is basically r, and this theta is basically this theta, right? So this is just another representation. This is what we call polar form of a complex number. This is just another representation of writing complex numbers. You can either write it this way or this way, okay? But for writing, are you clear with the background of the polar form?
Yes.
Okay, so I'll rub this. Okay, whenever you are preparing for an exam, like I'm not the type of I am always giving mathematical backgrounds whenever necessary, but just know that this is going to hold in general. Okay, and this r basically is z mod. Okay, and since z mod is under root real part square plus imaginary part square, so r is basically under root x square plus y square, and theta is the same angle. Theta is the argument which we discussed, y by x. So we know that if this is a complex number, we can write it this way as well in polar form, right? Okay, now we were talking about the theorem. So this is not the theorem. Basically, the theorem is a bit different. So basically, they are saying that if z is a complex number, and we have discussed this thing that um, it can be written this way as well, then you should know that z to the n is basically written as r to the n cos n theta plus iota sine n theta. Okay, I'll tell you. You can write this as well, cos theta plus iota sine theta, right? So far you only know that this is what a complex number is, and this is the polar form which we have discussed. Okay, so you have r cos theta sine theta, you know what r is, you know what theta is. And again, the question is that if you come across a big calculation like the one which we did in that question, x plus iota y to the x, let's say, in that case, now you don't have to do it this way. Okay, you don't have to do it this way. You can directly do it by basically finding the r. You have to write r to the n cos n theta plus iota sine n theta, right? So is this thing clear?
Yes.
Okay. Okay, so if you don't have to even know the name of this theorem, because you will be solving questions. So far, the final thing which we have discussed is very simple, that whenever you have a question where you need to find z to the power n, n could be 6, 10, 8, any number, you are going to do it this way. You need to first write down your z, that basically is r cos theta plus iota sine theta. This is the polar form. And then this n would basically come here, here, and here. Right? So is this thing 100% clear?
Oh, I was muted. Yes, it is clear.
Okay. All right. So anything which you would like to ask about the contents of this chapter which we have discussed today?
No.
No. Okay. Perfect. All right. So let me just take out the questions now. We have 10 minutes. We can do some of the questions. So I have shared the screen again. Are you able to see the screen?
Yes.
Okay. All right. Now, just give me a second, please. Just give me 1 second. I just need to see if we have covered everything. All right, yes. Okay. So the very first question is the set of rational numbers between two real numbers is, okay. Let's just draw our number line again. So we have 0 and 1. Since they're talking about two real numbers, we know that 0 and 1 are also real numbers. So we have infinite many numbers between these two real numbers, right?
Mm,
And if we talk about rational numbers particularly, we do have infinite many rational numbers between these two numbers. Let's say we have And what is the definition of rational numbers? A quick background.
The rational numbers.
Here we have the rational numbers, okay? Terminating or recurring. Okay, so if you look at the questions here, you know that between 0 and 1, you are going to have infinite many decimal numbers where the decimal is terminating, right?
Mm.
So this means
Yes.
that the answer is infinite. We have discussed this thing as well, okay? The question which you asked, that between two real numbers we have infinity and the boundary is one. Why is that possible? How is that possible in that thing? So is this thing clear?
Yes.
Okay, very good. Then the multiplicative inverse of a non-zero element A belonging to Z is, yes,
Mm-hmm.
yes, Samad, what is the answer? Multiplicative
C.
inverse. Okay, very well said, very well said. You are correct that multiplicative inverse is basically 1 by A into A, no doubt, but the set is of integers. In integers, we
Mm.
have like the negative numbers, then we have 0, and we have positive numbers. We do not have fractions, okay? So
Right.
multiplicative
So
inverse
D.
of a non-zero number, yes, it would be
Non-existent.
excellent. It would be D. Very well done. So, just be very, very careful about the set. D is the answer. Very
Okay.
well. Okay. Then we have the set X. In this set, we have X's, and these X's are basically real numbers. Okay. And we only have such X's which satisfy this. And what is this? X square plus 10 equals 0. Okay. So it is x square plus 10 equals 0. I can write it as x square equals minus 10, and I can write it
Mm.
as x equals under root minus 10. So this
Right.
basically is, what is the answer?
It would be minus 10.
Okay, look. The very first
Null
thing
set.
is, yeah,
Mm.
null set. Very well done. Why? Because here the answer is x equals under root minus 10. So I can write it as iota.
Mm.
First, I can write it as under root um, under root minus 1 into under root 10, and then I can write it as iota under root 10. Now I know that this iota under root 10 is not a real number, it is a complex number, and in this set I have real numbers only. Okay, this was the reason behind mentioning it this way, that they have specified that this x belongs to R, and in this R you have real numbers only. Now if you are defining your set this way you will get iota under root 10. Iota under root 10 is not a real number, so you do not have any real numbers in this set. So this means that this would be a null set. C is the choice, right? You get correct. Sorry, yeah. So is this thing clear?
Yes.
Okay. Then we have additive identity on n is, yes, now n is the set of
On N.
natural numbers. Yeah,
Integer.
n natural numbers. Okay, I'll show you.
Natural numbers. Okay. No
These are
identity.
very well done. These are natural numbers. We do not have any zeros, so no identity. Excellent. So no identity. Okay. Then additive inverse of 2 plus under root 3 is, yes, Samad, what is going to be the additive inverse?
A.
Okay, look. Here they are talking about
Mm.
additive inverse, not the conjugate. Okay, like this is not a complex number.
Okay.
Additive inverse is basically if A is a number, its additive inverse would be minus A. So you need to have minus here. So that would be -2 minus under root 3,
Okay.
right? So C
C.
would be the answer. Very good. Excellent. Okay. Then if we have the multiplicative inverse of under root 7 is,
Hmm.
now again multiplicative inverse. Multiplicative inverse of any number is such a number that when we multiply it with this number, we get the multiplicative identity, that is 1.
1.
So that number is
D.
D?
Okay, that's the answer. D is the answer, right? So
No.
it would be
Yeah. D is the answer, exactly. D would be the
hmm,
multiplicative identity. Yes. So
so it should be 1 by root by 7, right?
excellent. Yes. And you can't see that in answers, right?
Hmm.
So if you do this on calculator, you will see that this basically is B. Just check this on your calculator, and this holds for many numbers in maths. If you have 1 divided by under root 7, you basically have under root 7 by 7. Just check that on your own. If you have 1 divided by under root 2, you have under root 2 by 2. You can check that and then you will, get a better idea. This only holds for prime numbers, okay? Only for prime numbers. Whenever you have a prime number, 7 is a prime number, 1 by under root 7 is under root 7 by 7. Is this clear?
Okay, it only holds for prime
Prime
numbers.
numbers.
That's it.
Yes. I think
Okay.
that, when we are doing like in A levels maths as well, at times we get such answers which don't match the marking scheme, or the answers that are given at the end of the book. So sometimes this is the reason that 1 by under root 7 is basically under root 7 by 7, right? So this is
Hmm.
why our answers don't match, but technically our answer is correct. Okay. So we only have 2 minutes left. Just tell me if you are not clear with anything. I can explain that again. Any content, anything,
No.
everything is clear? Sure.
Yes.
Okay, very good. So I'll share all this with you. Okay. And we'll do rest of the questions tomorrow. Right. So I'll stop sharing this and I'll end the recording.